Okay, so we're going to start by just looking at an integration where partial fractions is useful, and then we'll look at how we might solve a problem which would involve partial fractions. So we'll start off with integral. Integral of 4 over 5x minus 3 with respect to x. The first thing to recognize that there is a standard integral that might help us. The integral of 1 over x with respect to x is, I suppose any of you remember it, do you? Or well, that's what x to the minus 1, that is x to the minus 1, Jordan, well done, yes, but what's the integral of x to the minus 1, or 1 over x? Standard integral, log x plus c. The natural log of x plus c. Remember, the natural logarithm is the logarithm to the base e, which is that natural number. And you know in lots of functions that you've come across in other topics, that exponential function occurs, doesn't it, in the decay of capacitors and so on, and we find that it often arises as a result of an integration like this. So it comes out as a solution naturally to some sort of integral, which is why it appears. So we're going to use that standard integral because this looks a bit like that. 4 over 5x minus 3. The x is underneath in the denominator in that fraction, and we've got the standard integral, the integral of 1 over x is log x plus c. But what do we do about the rest of it, the 5x minus 3? Well, let's have a look. So the first thing we can do with this is we could take the 4 outside the integral. We've done this sort of thing before, so that's just the 4 outside the integral leaves us what inside the integral? What about the fact that it's underneath in the denominator? What's going to go on top? Right, so 1. Because 1 times 4 gives us back our 4, and now it looks even more like that standard integral. It's 1 over something. What we do now is we make a substitution, so we use algebraic substitution, which is something we looked at last year. Substitution. We let u equal the bit at the bottom, the denominator, 5x minus 3. So now the integral becomes 4 times the integral of 1 over u. So now it looks even more like the standard integral. It's just got 1 over u because we've let u equal the 5x minus 3 bit. The only trouble is it's still with respect to x. So I can't do this integral because I'm still integrating with respect to x. So all I've done is substitute another letter to represent 5x minus 3. I still want to integrate with respect to x, so I can't do it. What I have to do is change my dx into du, and then I can integrate it. I want this to look like 4 times the integral of 1 over u du, and then it's just this standard integral here. The answer will be log u. So how do we do that? Well, we've got u equals 5x minus 3, so all we do is differentiate that to get du. So if u equals 5x minus 3, du by dx, differentiate it, is just 5, Phil, right. The 3 disappears, 5x becomes just 5. So we can see now we've got a du in there. what I want to do now is substitute into this integral here dx. Instead of dx, I want to write something. So all I do now is rearrange this to read dx equals something and treat it just like an ordinary algebraic expression. So multiply both sides by dx, and we've got that du equals 5 times dx, and then divide both sides by 5, and I've got dx equals du over 5. So to recap, just quickly, we've got an integral like this to do. So we're going to use tricks to do it, and tools, calculus tools and algebraic tools to try and solve it. We know this standard integral, so I want to get my integral to look like this. 1 over x with respect to x. So I'm integrating 1 over whatever x is with respect to that variable. And then the answer is going to be just log x plus the constant c. So all that follows is just to try and get it to look like this standard integral. So instead of 4 over 5x minus 3, I'm going to take the 4 outside the integral and call 5x minus 3 another variable. I'm going to call that u. So then the integral becomes that, 4 integral 1 over u. But I've just got to change this dx into du so that it then looks exactly like the standard integral. And how do I do that? Whatever I've called u, I just differentiate that and rearrange it for dx equals du over 5. So now I can, instead of dx, I can write du over 5, and the integral becomes 4 times the integral of 1 over u times du over 5. The 5 can come outside the integral because it's a constant. So this equals 4 over 5 integral 1 over u du. And now that is the standard integral. So this bit is now the standard integral that we've got at the top. So the solution is 4 over 5 times log u plus c. But what's u? 5x minus 3, so I just substitute that back in again. 4 over 5 log 5x minus 3 plus c. The fact I don't need to multiply the c by 4 over 5 because that's just a constant, so the constant is just multiplied by 4 over 5, so it's still a constant. Let's look at another example. Integral 3 over 5x squared plus 4 with respect to x. First step, take the 3 outside. Okay, next step. Right, u equals 5x squared plus 4, so we can write okay, next step, somebody else. Right, to change the dx into du, I've got to differentiate that. So as an aside, and we almost do this as an aside, write down what u is and then differentiate it. So who cares to do that integral for me? Answer? 10x, Tom. Bring the 2 down, times it by the number in front, take 1 to the power, 10x. Okay? Next step, rearrange for dx. Let Phil do all the work. Rearrange for dx, multiply both sides by dx, divide both sides by 10x. So effectively, you are bringing the dx up there to there and the 10x down there. So you're effectively swapping them over. So dx equals du over 10x. Now what do I do? Well, I've got to substitute in dx this, haven't I? So the integral now becomes 3 integral 1 over u times du over 10x. What can I do now? Take the 10 outside, however, that's supposed to be 2 exclamation marks. I don't quite know what it looks like, but it's supposed to be a couple of exclamation marks pointing at the x. Why have I done that? It's a variable, yes, not a constant. Exactly right, Tom. In other words, we can't do it. We're stumped now, okay? This method only works if we look back at the previous example, and you may remember the steps really well. Let's look at what we did. It only worked because when I differentiate, what happened? Got rid of the x, okay? So it only works if x is on its own. If it's x squared, x cubed, any other power of x other than 1, this method of substitution won't work. And we'd have to use another method to do it. So that's the first thing you do when you look at a problem like this and you're going to use this method, is you look at this here and check that that's only a linear function in terms of x. If it is, then you can use substitution to get rid of the x, okay? So this method only works if the denominator has a linear or is linear in terms of x. In other words, there's no x squared or x cubed, root x, anything like that. It's got to be linear. Because otherwise the x doesn't disappear. That x must disappear for it to work. Look at those 3 integrals. Can we use this method of substitution to do the first one, A? Because no x squared, anything like that. Can we use it in B? Yeah. So just x on its own, it doesn't matter whether there's a constant by it, it will work. What about the last one? Because if I times them together, I'll get an x squared term. Exactly right. Okay. So I want you to do those 2 integrals from the top 2. And then come up with an answer for them both. You've seen the shortcut. Let's look at these. Look at these solutions. If A is 1/3 log 3x plus 4 plus c, B is 3/5 log 5x plus c. If we look back at the first one that we looked at, here, the integral turned out to be, that was this one, wasn't it? Turned out to be 4 over 5 log 5x minus 3. So what's the shortcut? Yeah, that's right. If I look at this, if I differentiate this, I'm left with 3. And that goes underneath outside the integral, doesn't it? If I differentiate 5x, I get 5, and that goes underneath. So if I differentiate 3x plus 4, I get 3, that goes underneath. Differentiate 5x, I get the 5, which goes underneath. And if we go back to the first one, we would see that. So that works. So it's dead easy, as you say, there's a shortcut. You just look at it. If it's a linear function in terms of x, fine, it will work. And if it will work, all I've got to do is ask myself, what am I left with when I differentiate it? The 3, and that goes in the denominator underneath outside the log function with whatever happens to be on top. So in this case, it's 3 over 5 log 5x plus c. Okay? So once you see the shortcut, take the shortcut. But I wanted to go through it so that you could see when it works, when it doesn't work, and why it works. Okay? Well, you're not going to be doing an exam in this, but if you were, then I'd probably be looking for the steps. Yeah, yeah. So let's look at this one. This is doable. So this particular one here, you're dead right in saying that if I were to expand out those brackets, then it would be an x squared underneath, so this method wouldn't work. However, there is a way around it. What we do is we use the method of partial fractions to split this up so that it's some number over 2x plus 1 plus another number over 3x plus 2. And then we integrate each one separately following exactly the method that we've just been doing. So you can do this, but first of all, you have to use partial fractions to separate out the denominator. So that's what I want to look at now. Okay, so the method of partial fractions then is a way of getting a fraction to look like this. Two fractions, one underneath the one in terms of one denominator, the x, plus another fraction with the denominator y. If I wanted to multiply these together, let's sort of look at how we can get this to be combined. So the way I'm going to try and show you how this works is to sort of think of it in reverse, really. So this is the answer that we're sort of heading for. We want to separate these fractions. So, but if I wanted to combine them, what would I do? What's the process to combine these two fractions together? If I wanted to add them together, what must be true to be able to add fractions? The denominator must be the same. What's the common denominator for this? xy. So I've got to get this first one to be xy underneath, so what would I do? Pardon? Times by y to get xy. So what do I do to the top? And what about this one? Right, okay. So in other words, if I were to do that, I would then have a common denominator, and I could say this equals 3y plus 4x over xy. And to try and get back from here, this form, to there, is the method of partial fractions. How to separate out a fraction with just one denominator like this back to its original components again. Easy for this one because we would just separate out the denominator and call it over each term. 3y over xy plus 4x over xy, and then I'd cancel out the y's and the x's and have it. What about something like this? If I wanted to turn that into a one fraction with one denominator, what would I do? Oops. Oh, it's going to go anyway. What about this one? So what would I multiply x minus 2 by? X plus 1. So what would I have to times the top by? Okay. But it would in fact be 1 times that, wouldn't it? What about the next one? Okay. In other words, we do exactly what we just did for the other one. Now what can we do? Well, we've got a common denominator at the bottom, so what can we do about that? All over x minus 2, x plus 1. And what can I now put at the top? X plus 1 plus 3 times x minus 2. Yep, exactly what we did on the previous slide. Now, multiply out the bracket at the top and then collect together like terms, and what do we get? X plus 1 plus 3x minus 6 over x minus 2, x plus 1. Collect together like terms, 3x plus x is 4x, 1 minus 6 is minus 5. All over, let's multiply out these brackets. X times x gives x squared, x times 1 is x, minus 2x is minus x, minus 2 times 1 is minus 2. And we end up with that. Through. So let's look at this, okay? Go back to the beginning of this one. We had 1 over x minus 2 plus 3 over x plus 1. We've multiplied, we've found a common denominator by multiplying the first one by x plus 1 and the second one by x minus 2. Then we combine them together and we've ended up with this. So in other words, 4x minus 5 all over x squared minus x minus 2 equals 1 over x minus 2 plus 3 over x plus 1. Now this is where today's session comes into it. I'm asked to integrate this with respect to x. And I look at it, I can't do it as it stands. However, that's the same as this. So this becomes the integral of that with respect to x plus the integral of this with respect to x. And that we can do. We just looked at those. That's trivial. We write down that answer. What is the integral of 1 over x minus 2 with respect to x in light of what we've just been doing? Yeah. Just you have to do this bit, Tyler. So you remember this? This becomes the u. So what's the differential of x minus 2? What I'm asking here, Tyler, is how do we integrate something like this? Can't do it as it stands. But if I could get this to look like this, because remember this is the same as this, then I could integrate this because that's easy. I just looked at some examples of this. This is just log, natural log. Remember, if I differentiate this, that number goes underneath in the denominator, doesn't it? Well, that's just 1, so it's just a log of x minus 2. What's this one? 3 log x plus 1 plus c. So if I can get this to look like this, then the integral is trivial. I just write the answer down. So the method of partial fractions is getting this to look like this. Yeah, sure. Well, I've got a tissue here, Jordan. Okay. So, what do we do it? What do we do? x squared minus x minus 2. Yeah. Just one over x minus 2 plus 3 over x plus 1. Right. What do you want to go back to? That. Bill? Yeah. I mean, Jordan? Yeah. Plus 1. In other words, that, isn't it? Zach, happy? Right. So how do we get from there to look 4x minus 5 over x squared minus x minus 2 to look like this? We factorise the x squared minus x minus 2 to get the two linear factors, x minus 2 and x plus 1. Then separate these terms, and this is the method of partial fractions we're going to look at. That's to allow us to find these numerators 1 and 3. So that's the process we're going to be looking at. So remember factorising the first bit. How do we get from the x squared minus x minus 2 to these two linear factors? We factorise two numbers that multiply together to give minus 2 and add together to give minus 1. Minus 1x, the number there. Multiply to get minus 2 and add to get minus 1. Answer? Right. Minus 1 plus 2, no, minus 2 plus 1, isn't it? Yeah. Minus 2 plus 1 gives us minus 1. Minus 2 times 1 gives us the minus 2. So the first thing is to remind ourselves, how do you factorise? That's what you do. Okay? And now you separate out my two linear factors, x minus 2 plus something over x plus 1. And now we're into this method of partial fractions. We separate out the two denominator, the two terms in the denominator, the x minus 2 term and the x plus 1 term. And then we've got to find these two missing numbers. So what we do is we call them A and B. If I had 3 factors underneath here, then I'd have A, B, and C, and so on. And when you get to look at the problems, which you will be doing shortly, it's a case of just trying these different methods. So now, if you think back to the case where we had 2 fractions and we were adding them together like this, what did we do? We multiplied the bottom denominator in the first one by the denominator in the second one to get the two together. So what we did was, we said this equals something over x minus 2. So if I times that by x plus 1 to get this one to look the same as this one, what have we got to times the top by? X plus 1. So I'd have A times x plus 1 on the top, plus x plus 1 has got to be multiplied by x minus 2, right? So I must multiply B by x minus 2. We're using the same idea we did to combine them. So now, the right-hand side equals something over x minus 2 x plus 1, all over the same denominator. And now I can just write this on the top. A x plus 1 plus b x minus 2 goes on top. So just to recap here, let's look at this. We've taken our original problem. Here it is. First step, factorize it to get the denominator in terms of linear factors. Because remember, this whole method of integration only works if we've got x without any power in it. So we've got to convert this into linear factors. Once we've done that, we separate out these two factors in the denominator like this. And we say to ourselves, well, we don't know what these numbers are, but there must be some number on the top and some number at the top for both of these factors. What are they? So then we focus on this right-hand side and we say, right, let's try and recombine these actually. So go back to one denominator underneath. So I have to multiply the x minus 2 term by the x plus 1 to get this one. And I have to multiply the x plus 1 term by the x minus 2 to get this. So then the denominators are the same. But whatever I do to the bottom, I must do to the top in both cases. So I end up with this. Sorry? Right, what we say now is, don't forget we're only looking at the right-hand side, Tom. Good question. So what we now say is, well, actually, this equals 4x minus 5 over x minus 2 x plus 1. And now we look at this and we say, look at the left-hand side, look at the right-hand side. The denominators are the same in both. It's both of the denominators are x minus 2 and x plus 1. Because of this equal sign, that means these fractions must be exactly the same. So if the denominators are the same, so must the numerators. So we equate numerators. And we say, that looks like an N, doesn't it? Numerators. So we can write 4x minus 5 equals a x plus 1 plus b x minus 2. I'll just pause. Now we multiply out the brackets on the right-hand side. So 4x minus 5 equals ax plus a times 1 is a, plus bx minus 2b. So we multiply out the brackets. And then we collect together like terms on the right-hand side. We look at this and we actually collect together the x's. So if I take x outside a bracket, I've actually got a plus b x. And then finally plus a minus 2b. So we collect together the terms involving x. So it's a plus b, lots of x. That's quite an important step, so just have a look at that and see how that works. So we can write 4x minus 5 equals that. But because, again, the left-hand side equals the right-hand side, if we look at it, that means that any term involving x on the left-hand side must be the same on the right-hand side. So a plus b, the coefficient of x on the right-hand side, must be 4. The coefficient of x on the left and right must be the same. Any constant, any number on the left-hand side, minus 5, must equal the constant on the right-hand side. So a minus 2b equals minus 5. So by equating coefficients, it's called, we can write two equations. a plus b equals 4, and the second equation is a minus 2b equals minus 5. 1, 2. Can you see how important it is now to, when we got to here, that we separated out the terms involving x. So we got ax plus bx leaves us a plus bx. So we factorize that bit and get the x terms and then the rest, so that we can then equate coefficients. And we can write that a plus b equals 4, a minus 2b equals minus 5. Two equations, two unknowns, simultaneous equations. Okay? So we can, well, we could do it a couple of ways. We could either make the a's and b's the same, which they are, actually, because we've got a in both, and take one equation from the other. Or, if it's a bit more complicated, we could maybe rewrite one of the equations, for example, number 1, to read a equals something. So a equals 4 minus b, and then in equation 2 we could substitute in 4 minus b instead of the a, and we'd only have b's. That's the more general method. So instead of making them the same, we could try doing it that way. So either by substitution or by elimination, we can find a and b. So just see if you can do that. I'll just pause it a sec. Okay, I'm just going to look at both the methods, elimination and substitution. I want to look at both because it's not always easy to do it by elimination. It's not always easy to do it by substitution. So being aware of both methods is useful. So first of all, let's do it by elimination. Well, a's are the same in both of those, so I'll probably use elimination in this particular case. I'm just going to subtract 1 from 2 or 2 from 1. If I do 1 take away 2, I'm going to have b minus 2b is plus. So that's going to give me positive values, so that's good. So I'm going to do equation 1 take away equation 2, which will mean I have a minus a is 0, b minus 2b, b minus 2b is plus 2b, gives me 3b, equals 4 minus is plus 5, so 9. 3b equals 9, so therefore b equals 3. Once I've got that b equals 3, I can substitute that into, let's use red, substitute in 1, the easiest one. So if b equals 3, then a plus 3 equals 4. So a equals 1. I could then check in the other one to check it works, okay? By substitution, let's just have a look at this. What I do is I rearrange number 1, as I indicated, to get a equals 4 minus b, and then I substitute this into number 2. So, in 2, or substitute in 2, our value for a, which is 4 minus b, I get a, which is 4 minus b, minus 2b equals minus 5. So I've only got b's now, so I can solve it. 4 minus b minus 2b is minus 3b equals minus 5. So taking the 4 over the other side, well, actually take the 3b over the other side, I'll get 4 equals 3b minus 5. Adding 5 to both sides, I get 9 equals 3b. So therefore b equals 3, and same answer. Okay. Sometimes you'll find elimination is better, sometimes substitution. Don't ignore the substitution method. So back to the original problem, we have this. Look, we took our original integral that we were trying to do, remember. We separated that out into its linear factors, and then we were trying to find these values for a and b, which we've now done. So therefore, the integral of 4x minus 5 over x squared, what was it, minus x minus 2 with respect to x equals the integral of a, which turned out to be 1 over x minus 2, plus b, which was 3 over x plus 1 dx. Sorry? I'm not quite sure what you see there, what you're saying there, Tom. Hang on. So now we've got to this. We've used our method of partial fractions to get to here. Now, as we showed earlier, that's now straightforward to integrate. Let's look at one more example. You tell me what to do, and then I'll leave you at a certain point to finish it off. So let's start this off together. First step, factorize it. Right. How do we factorize? Two sets of brackets. So what have we got? Two numbers that add together to give minus 2 and multiply together to give minus 3. Add together to give minus 2 and multiply together to give minus 3. What will they be? Plus 3, negative 1 will give us plus 2, so that's the wrong way around, Tom. Yeah, minus 3 plus 1, yeah. Minus 3 plus 1. Minus 3 plus 1 gives minus 2. Minus 3 times 1 gives minus 3. So there are two factors, okay? So I'll just pause this here. You see if you can finish that off.